in 2010. Okay, in 2010 this problem came. Okay, fine. This is our question 4. It says limit as x tends to 0, 1 upon x squared into definite integral from 0 to x t upon t raised to 4 plus 1 dt. Okay, now there could be two ways to solve this problem. First, by evaluating the definite integral, and second, without evaluating the definite integral. Any way you can choose. And suppose we wished to solve this problem by evaluating the integral first. Well, I'm not going to do that, but I will give you that as homework. Okay, so how will you evaluate the integral? Can you tell me, please? Will you evaluate the integral? You will choose the substitution t squared equal to u. Why t squared equal to u? Because the derivative of t squared in its variable form is available there, right? So t dt would be half du. Is it clear? T dt would be half du. Yes, and then what would be the limits? Okay, sorry, not x, t and u. T0, u0, and if t is, sorry, t0, u0 there. And if t is x, what would be the limit on u? It would be x squared. Okay, it will be x squared, and then I think its integral will be something tan inverse. So you can go for it. Okay, so I'll leave this part to you. I'm going to choose the other method, which is not evaluating. So then how are we going to solve it? Okay, the integral, okay, by not evaluating the integral. So let's think about it now, like what can we do to solve that particular problem without using the evaluation or the value of the integral. Look, at the end of the day it is a limit problem. Okay, with 1 upon x squared sitting outside the integration, that is a clear indicator that we should be going for L'Hospital's rule, if at all it applies, right? And if we choose 0 here, then we'll get 0 there, but also that will make the limits on the definite integral same. Okay, that will make the limits on the definite integral same, and therefore it will be in the 0 by 0 form, and therefore L'Hospital's rule is applicable. Okay, so tell me now, if we apply the L'Hospital's rule, there is no question of the regarding the derivative of the denominator, that is 2x, isn't it? That is 2x. How will you now go for the derivative of the integral? Remember, I told you a rule which we called DUIS, differentiation under the integral sign, or we also call it Leibniz rule sometimes. And what do we exactly do there? First, what do we do is we keep the limits and this part as it is, and we take the partial derivative of this with respect to not t but with respect to x. Okay, because we are differentiating with respect to x, and because there is no term in x in that function, I will write it as 0. Then what next? What follows is we put the upper limit there. What do? We put the upper limit there, and we multiply this by the derivative of the upper limit with respect to whatever variable we are differentiating it with respect to, right? So that's x, so derivative of x with respect to x is 1. Okay, then we go to the lower limit. We substitute it in the integrand. Anyway, we are getting 0, but we again multiplied by the derivative of the lower limit with respect to x, so that's 0. Okay, have you understood till this? if you see any other solution, they would directly go for this, okay, without clarifying how did that come. But that is actually the differentiation under the integral sign. The first term is the partial derivative of the function of t with respect to x. For x, t is a constant. So that's it. Okay. Okay. So what is the good news now? The good news is x will get cancelled. You've got this 2x here. We've got this x here. Okay. And x raised to 4 plus 1 will come in the denominator. X will go. And the final answer is 1 by 2. 1 by 2 is option C. Okay. The option does not exist. That, well, that might lead to some confusion, because if we see all numbers as all 4 options, then we know that the limit exists. So anyhow, that rule will be applicable. Fortunately for this case, we were not required to argue anything about with the applicability of the lost base rule. One reason is the function t upon t raised to 4 plus 1, that is a good function in the sense it never becomes undefined, okay, nowhere near 0, or rather it's throughout its domain it never becomes 0, like, because it has t raised to 4 plus 1 in the denominator. So as far as the applicability of the rule is concerned, we know it's very well behaved. Okay. And secondly, although x is tending to 0, we have x squared there in the denominator. Okay, we've got x squared here, which again says no matter from which direction we have that x approaching 0, x squared will always go to 0. Okay. Okay. Now let's verify it now on Desmos. It also does all that stuff also. Okay, so how to verify that? Look. What can we do is we can go for 1 upon x squared first into integral from 0 to x, okay, t upon t to the power 4 plus 1 dt. Okay, so this is how the function is, right? This is how the graph of the function looks like. And we have got our value as 1 by 2. Let's see if it is there. Clearly it's 1 by 2 because this is rounding it off. But at 0 we should get it undefined. Okay, yeah, see, look. At 0 we got undefined, but near that, everywhere it is 0.5. So see, at point 2 it's not 0.5. This calculator is rounding it off to 0.5. Okay? Okay, so you can also use Desmos to evaluate integrals. It's a good tool to have.